What if I told you that the energy source humanity is most terrified, the one that conjures up all those images of glowing apocalyptic wastelands and, mutant monsters, has actually saved millions of lives by quietly preventing invisible air pollution?
It sounds totally contradictory, right? But it's true.
It really is.
Right.
Today, we are opening the ultimate Pandora's box in this deep dive. We're talking about nuclear power. We're stripping away the politics, looking at the raw physics, and answering the questions you actually care about without needing a PhD to follow along.
And honestly, it is the perfect topic for us to dig into today because there is, there's virtually no middle ground in the public imagination when it comes to nuclear energy. It's usually framed as either this utopian clean energy savior that will rescue us from a warming climate
Or it's a ticking time bomb just waiting to render a continent uninhabitable.
Exactly. There's no in between.
Okay, let's unpack this because right out of the gate, we need to set some ground rules for you listening. Neither of us is taking a political or ideological side today. At all.
Yep.
Our mission in this deep dive is simply to impartially report on the factual physics, the historical data, and the very honest trade-offs of this technology. We are laying out the ledger, the cold, hard pros and cons, so that you, sitting there right now, have the actual mechanisms and facts to do your own weighing up.
And that approach is just so vital because nuclear power is, it's the ultimate example of a subject where thoughtful, well-informed people can look at the exact same set of physical facts and reach completely opposite conclusions.
Right, because the science is what it is.
Exactly. The raw data of how a reactor works doesn't change, but how human beings interpret the risk of that data, that changes drastically based on what we inherently value and what we fear.
So before we can even begin to debate the safety or the politics or, the environmental footprint, we really have to start at the foundation. We need to understand the extraordinary, almost unbelievable mechanics of where this energy actually comes from.
Yeah, we have to start with the atom. And we are going to take this nice and slow because the physics here are, they're mind-boggling when you really look at them.
They really are.
So everything in the universe, the device you are listening to this on, the air in the room, your own body, it's all made of atoms. And at the very center of every single atom is this tiny, incredibly dense core called a nucleus.
It's like the heavy architectural center of the atom, basically.
Precisely. And inside that nucleus, you have a cluster of particles. And for our purposes today, we really only care about the neutral ones, which are called neutrons. Now, most atoms are perfectly stable. They just exist. But in certain very heavy, massive atoms, the nucleus is large and just a little bit jittery.
Like unstable.
Yeah, just a little bit unstable. And uranium is the absolute workhorse here. If you take a specific type of uranium atom and you fire a single stray neutron at it, like a microscopic bowling ball hitting a pin, the nucleus can actually split right in two.
It just cracks down the middle.
It does. And this specific process is called nuclear fission. And whenever you hear that word fission, don't let it intimidate you.
It's a heavy sci-fi word, though.
It sounds like it. But it simply means splitting. Nuclear fission is literally just splitting the nucleus. But here is the magical part. When that nucleus splits, two vital things happen. First, it releases a massive burst of energy.
Okay, why?
Because if you put the two new broken pieces on a scale, they actually weigh very slightly less than the original whole atom did.
Wait, mass just vanishes. Where does it go?
It doesn't vanish, it transforms. That tiny, almost imperceptible amount of missing mass is converted directly into pure energy. And because the speed of light is squared in that famous Einstein equation you've probably heard of, even a microscopic amount of mass equals an astronomical amount of energy.
Wow.
Right. And the second thing that happens when it splits is that it spits out a few more loose neutrons.
Oh, I see. And those extra loose neutrons are the spark for the whole engine. Because they go flying off and they slam into other neighboring uranium atoms, which then split, release their own burst of energy, and spit out more neutrons, which hit more atoms and so on.
You've got it. It creates a chain reaction. That chain reaction is the entire reason nuclear power is worth all the extreme engineering trouble. The energy locked inside that nucleus is millions of times denser than the energy found in, normal chemical bonds.
When you think about our traditional power sources, it really puts this into perspective. Because we are so used to burning things for power, wood, natural gas, coal. But if I'm getting this right, burning a lump of coal is really just lightly rearranging the outer furniture of an atom, its electrons. It's surface-level chemistry. But splitting a nucleus, that is tapping into the mighty architectural foundation of the universe itself. The scale of it is just hard to wrap my head around.
That is a brilliant way to picture it. You are bypassing the furniture and striking the very foundation. And the math completely reflects that reality. A single kilogram of uranium fuel can release as much energy as millions of kilograms of coal.
A kilogram. That's what, roughly the weight of a bag of apples at the grocery store, equaling massive freight trains full of coal.
Yeah, that absurd energy density is the entire appeal of the industry. You get enormous, continuous, reliable power from a comically tiny amount of physical fuel. And crucially, because you are splitting atoms instead of setting fire to carbon, there is absolutely zero carbon dioxide produced by the reaction itself.
Okay, I understand the splitting atom. The chain reaction makes sense. But how do we actually capture that foundation-shaking energy and turn it into electricity to charge my phone or power a city? Because the engineering always sounds impossibly futuristic, but the text says the actual mechanism is basically, well, a kettle.
A very sophisticated, multi-billion-dollar kettle. Yes. Yeah. The whole art of a nuclear power station is just controlling that atomic chain reaction so it ticks over steadily, generating a tremendous, consistent amount of heat.
So we're just making heat.
Exactly. That heat is transferred to water. The water boils and creates high-pressure steam. The steam is pushed through pipes to spin a giant fan blade called a turbine, and that spinning turbine spins a magnetic generator, which creates electricity.
Wait, so the back half of a nuclear plant is exactly the same as a 19th century coal plant, just steam spinning a wheel?
Fundamentally identical. The only difference is the furnace. Instead of lighting coal on fire to boil the water, we are splitting uranium atoms to boil the water.
Okay, but this raises the exact question that terrifies people. Here's where it gets really interesting. If we are relying on a chain reaction of splitting atoms, throwing off neutrons that split more atoms in a compounding loop, why doesn't this sophisticated kettle just detonate like a nuclear bomb?
It is the most natural question in the world. Everyone wonders that. And what's fascinating here is that a nuclear detonation in a commercial power reactor is actually physically impossible. Like, it literally cannot happen by the very laws of physics.
I have to stop you there, because the public perception is absolutely that these places are ticking bombs. Why is it physically impossible? What is the actual difference between the reactor and a weapon?
So think of weaponized bomb-grade uranium, like a pile of highly explosive dry gunpowder packed tightly into a sealed steel barrel. The explosive atoms are highly concentrated or enriched to force a runaway instantaneous explosion.
Okay, all packed together.
Right. But reactor fuel is fundamentally different. It is barely enriched at all. It would be like taking that dry gunpowder, mixing it with huge buckets of sand, and spreading it out over a wet lawn. It can absolutely burn, and it can generate a lot of heat, but a chain reaction explosion is physically impossible. The atoms simply aren't packed densely enough to detonate.
So the fuel itself is just the wrong recipe for an explosion.
Exactly, the wrong recipe. And beyond the fuel, a reactor has physical brakes. They use what are called control rods. These are long rods made of specific materials like boron or cadmium that absolutely love to soak up neutrons. Think of them like a sponge soaking up water.
Okay.
If the reactor is getting too hot, the human operators or the automated safety systems slide these control rods down into the core. The rods absorb those bouncing neutrons, starving the chain reaction and slowing it right down. If they need more power, they pull the rods up a little bit, letting the neutrons fly freely again.
You literally steer the heat of the reactor by sliding these metallic sponges in and out.
Yeah.
Okay, you've convinced me a commercial reactor can't detonate like a nuclear weapon. The physics don't allow it. But I watched the news in 2011, and I know Chernobyl blew a literal hole in the roof in the 1980s.
Yeah.
If the physics don't allow a nuclear explosion, what exactly blew up?
We absolutely have to talk about the accidents, because dread of these specific events drives the entire global conversation on this. Let's start with Chernobyl in the Soviet Union in 1986, because it is the ultimate worst-case scenario. It was not a nuclear detonation. It was a massive steam explosion.
Steam. It blew the 1,000-ton roof off the reactor with just steam.
Yes, because Chernobyl utilized a fundamentally flawed reactor design that simply wouldn't be legally allowed to operate in most of the world today. In a standard modern reactor, if the cooling water boils away, the nuclear chain reaction naturally slows down. The physics inherently pump the brakes.
Right, the water is part of the process.
Exactly. But Chernobyl's specific design had a fatal flaw. If the water turned to steam, the nuclear reaction actually sped up.
Wow, that sounds incredibly dangerous.
It was wildly dangerous. And then you add to that flawed design a catastrophic human element. The operators were running a highly reckless late-night test, overriding and actively disabling the automated safety systems. Yeah. The reactor surged, the water instantly flashed into steam, and the immense pressure of that expanding steam blew the reactor apart. It then caught fire, spreading radioactive material across Europe. It killed dozens of plant workers and first responders directly, and is estimated to have caused additional cancer deaths in the population over time.
So a perfect storm of bad engineering and terrible human judgment. But what about the accidents in democracies with strict regulations, like 3 Mile Island in the United States in 1979?
Right, at 3 Mile Island, a reactor did partially melt down due to equipment malfunction and operator confusion. But the crucial mechanism to understand there is containment. American reactors were built inside massive reinforced concrete and steel domes designed to hold in pressure and radiation if everything went wrong.
And did it work?
It did. The core melted, but that containment structure did its job. It held. Essentially, no measurable physical harm came to the public. It was a financial disaster for the operating company, obviously, but it was not a public health disaster.
Okay, but then you have Fukushima in Japan in 2011, and that was a modern, high-tech society.
Fukushima is a vital case study, but it was triggered by an unprecedented natural disaster. A massive historic earthquake and a subsequent tsunami breached the seawalls and flooded the plant. Now the reactors actually shut down automatically when the earthquake hit. The control rods dropped in, fission stopped.
Wait, if the splitting stopped, why did it melt down?
Because of something called decay heat. Even when you completely stop the chain reaction, the radioactive byproducts left behind in the fuel rods are still intensely hot. It's like turning off an electric stove. The burner is still hot enough to burn you long after the dial is at 0.
Right, that makes sense.
Those fuel rods need a constant flow of fresh cooling water for days after a shutdown, but the tsunami flooded the backup diesel generators. Without power, they couldn't pump the water. The water boiled away, the rods overheated, and they melted.
But the outcome of Fukushima is where our assumptions really get challenged, because the death toll from that event was horrific.
The death toll from the tsunami was horrific. Upwards of nearly 20,000 people died from the wall of water. But strikingly, the radiation released from the Fukushima reactor meltdowns is thought to have directly killed very few, if any, people.
Wait, really? I have to push back there?
Yeah.
You saying a triple reactor meltdown didn't cause the massive death toll we associate with that disaster?
It did not. The tragedy of the nuclear element of Fukushima is that the frantic, panicked evacuation of hospitals and nursing homes caused significant real harm. Moving highly vulnerable people rapidly in the chaotic wake of a natural disaster resulted in numerous deaths. The psychological terror of the radiation caused far more immediate human damage than the physical radiation itself.
That psychological mismatch is so stark. It feels perfectly aligned with our fear of flying versus driving. We get into our cars every single day without a second thought, even though the statistics clearly show driving is incredibly dangerous. But we get on a commercial flight, which is mathematically one of the safest environments on Earth, and we grip the armrests in absolute terror because we are picturing a dramatic, named disaster. A plane crash makes global news, but a car crash doesn't.
If we connect this to the bigger picture, that flying versus driving analogy is perfectly mirrored in how we view energy. If you tally up the actual documented deaths per unit of energy produced over the last several decades, nuclear power turns out to be one of the statistically safest sources of power humanity has ever invented.
Wait, safer than fossil fuels?
Oh, it is vastly safer. Nuclear's safety record is essentially comparable to wind and solar power. Meanwhile, oil, gas, and especially coal quietly kill massive numbers of people every single year.
Through air pollution.
Exactly. The World Health Organization attributes millions of premature deaths annually to respiratory illnesses caused by air pollution, which is heavily driven by burning fossil fuels. But those deaths don't come in a sudden, terrifying event with breaking news coverage. It's a quiet, invisible, daily pollution. So we just accept it.
Yeah.
We don't fear it the way we fear a reactor accident.
All right, let's assume the safety statistics hold up. Let's assume the day-to-day operation is incredibly safe. There is still a giant glowing elephant in the room that makes even the most data-driven people uncomfortable. The waste. The 1,000-year trash. Because fission leaves behind radioactive byproducts that remain dangerously lethal for tens of thousands of years. It just feels inherently irresponsible to create a substance that must be safely isolated for longer than human civilization has even existed.
It is a profound geological scale responsibility, no doubt about it. But if we're looking at the honest ledger, we have to contextualize that waste with two crucial facts. First, the sheer physical volume. Because uranium is so insanely energy dense, the actual amount of waste left over is remarkably small.
How small are we talking?
All of the high-level radioactive waste produced by a major country's entire fleet of nuclear power plants over several decades can fit into a surprisingly modest space, like a single warehouse.
Hold on. You say it fits in a warehouse, but that feels like a statistical trick to minimize it. It might be small in volume, but it's highly toxic for millennia. How is it somehow better just because it takes up less physical space?
Because being small and solid means you can physically contain it, monitor it, and control it. Compare that to a coal or gas plant. They don't store their waste in a warehouse. They pour billions of tons of invisible planet-warming carbon dioxide directly into our atmosphere, permanently altering the global climate. The nuclear industry is entirely unique because it physically contains and financially accounts for every single ounce of its own waste.
Okay, I see the distinction. One is solid and contained, the other is gaseous and dumped in the sky. But what is the actual solution for the radioactive rods? We can't just leave them sitting in a heavily guarded warehouse for 10,000 years.
The technical solution is a scientific consensus deep geological storage. You take the spent fuel, you seal it inside incredibly robust, multi-layered containers made of vitrified glass, thick copper, and cast iron. Then you bury it deep underground in geologically quiet rock formations.
So just burying it.
But carefully. We are talking about bedrock that hasn't shifted, fractured, or seen groundwater flow in hundreds of millions of years.
Out of sight, deep below the biosphere.
Exactly. And countries like Finland are literally building these permanent repositories right now. The hurdles to nuclear waste storage haven't really been technical or scientific. They have been almost entirely social and political, the whole not in my backyard sentiment.
Which brings up a great point about where we go from here. Because if the hurdles are massive costs, long build times, and political opposition, how does the industry survive? What is the live frontier of this technology?
The focus right now is shrinking the scale. The industry is developing what are called small modular reactors, or SMRs.
The idea being that instead of spending 15 years building a massive custom-designed $10 billion cathedral of a power plant, you build smaller, standardized reactors on an assembly line.
Right. You build them in a factory, ship them on a truck, and plug them in. It aims to solve the staggering financial costs. But crucially, SMRs are engineered with a massive leap forward in physics called passive safety.
How does that work? How is it different from the pumps at Fukushima?
So remember how Fukushima failed because the backup diesel pumps lost power and couldn't circulate the cooling water?
Right, the tsunami knocked them out.
Passive safety designs don't rely on electronic pumps or human intervention. They rely on the unchangeable laws of physics, like gravity and natural heat convection. Hot water naturally rises, cold water naturally sinks. If a passive SMR loses all power and every human operator walks away, the reactor is designed to automatically cool itself through this natural circulation of water, safely shutting down without a single pump ever turning on.
Wow, so it takes human error and mechanical failure completely out of the equation.
Oh.
Though it is worth noting that many of these SMR designs are still unproven on a wide commercial scale, mostly just sitting on the drawing board or in early prototype phases.
That's true. It's early days.
And then, beyond SMRs, there is the ultimate dream, the holy grail of energy fusion.
Oh, fusion would change the course of human history. Everything we've talked about today, splitting heavy atoms like uranium, is fission. Fusion is the exact opposite. It is what the sun does. It involves taking very light, abundant atoms, like hydrogen isotopes derived from seawater, and crushing them together under immense pressure and heat until they join or fuse into a heavier atom.
And releasing monumental energy in the process.
Staggering energy. But the brilliance of fusion is that it produces virtually no long-lived radioactive waste, and a meltdown is physically impossible because the moment the conditions drop, the reaction just instantly stops.
But it remains incredibly difficult to sustain, always 30 years away, as the running joke in the physics community goes.
Right. Sadly, yes. Creating a star in a magnetic bottle on Earth is arguably the hardest engineering challenge humanity has ever attempted. It remains out of reach for the commercial grid right now, which means we have to make our decisions based on the technology we actually have today. Fission.
So let's do what we promised at the beginning. Let's lay out the honest ledger, impartially.
Okay, in favor of nuclear power, it generates massive amounts of electricity with almost zero carbon emissions. It is highly reliable, providing baseload power 24 hours a day, 7 days a week, regardless of whether the wind is blowing or the sun is shining. It requires a tiny footprint of land, incredibly small physical amounts of fuel, and statistically per unit of energy produced, it is exceptionally safe.
And against nuclear power, these traditional plants are enormously expensive to build, constantly running years behind schedule and billions over budget. The solid radioactive waste requires active stewardship across geological timescales. The enrichment technology overlaps uncomfortably with concerns about nuclear weapons proliferation. And crucially, while a severe accident is statistically incredibly rare, if a meltdown and containment breach does happen, its consequences can spread across international borders and render land unusable for generations.
That's the ledger.
So what does this all mean? We started by saying nuclear energy is often painted in broad strokes as either a clean miracle or a glowing menace. What we found by actually looking under the hood is that it is neither. It is simply a tool, a piece of technology of extraordinary foundational energy density that demands profound, unwavering responsibility.
This raises an important question, and it's one we want to pass directly to you, the listener. We've seen today that the cold, hard data shows nuclear power is statistically incredibly safe and mathematically vital if we want a highly reliable, low-carbon future. But we've also seen that human psychology is deeply, understandably wired to dread the rare, catastrophic event like a reactor meltdown far more than the invisible daily harm of fossil fuel pollution.
Right.
So how do you balance it? When you look at the future of our world, how do you weigh the massive financial cost of building these reactors against the ticking, irreversible clock of climate change? How do you balance your natural human dread of a rare accident against the hard statistical safety data? Ultimately, choosing between these paths isn't just a math equation. It isn't a purely scientific question. It is a profoundly human one, based on what we value most and what we fear most. Will our future energy grids be determined by cold, hard statistics, or by our deeply ingrained human psychology?
It is a profound question worth carrying with you. Thank you so much for joining us on this deep dive today. Keep asking questions, keep looking past the caricatures, and keep exploring the fascinating, complicated mechanisms of this world we share. We'll see you next time.